Welcome to our deep dive into the world of variational quantum circuits, VQCs for short. We're going to be unpacking an essay by Jörg Pat. The title's a bit of a mouthful. It's called VQCs, Variational Quantum Circuits for Chi-I und Optimierung.
Yeah, that's German for VQCs for AI and optimization.
Exactly. It's a pretty dense topic, but trust me, it's worth wrapping our heads around.
Yeah.
Because we're talking about the potential to solve problems that are impossible for even the most powerful computers today.
That's right. And what's so intriguing about VQCs is that they manage to combine the mind-bending power of quantum computers with the reliability of good old-fashioned classical algorithms.
So it's like having a superpowered engine, but needing a skilled driver to control it.
That's a great analogy. Think of it this way. You have a problem you want to solve. Maybe designing a new drug or optimizing a complex delivery route. Instead of tackling it head-on with a classical computer, you turn to a VQC. Now, this VQC has a quantum part. We call this the circuit. And this circuit is capable of exploring a vast number of possibilities simultaneously, thanks to those quirky quantum phenomena like superposition and entanglement.
Okay, I'm already getting lost in the quantum jargon here. Can we back up a bit? What exactly are superposition and entanglement, and why are they such a big deal for computing?
Absolutely. Imagine you're flipping a coin. Classically, it can be heads or tails, right?
Right.
But in the quantum world, that coin can be both heads and tails at the same time until you actually look at it.
Whoa.
That's superposition. It's like the qubit. The basic unit of quantum information is exploring all possible states at once.
So instead of flipping one coin at a time, we've got millions flipping simultaneously. That's got to speed things up.
Exactly. And then there's entanglement, which is even weirder. Imagine two of those coins linked in a way that even if you separate them by miles, flipping one instantly determines the state of the other.
Whoa, that's spooky action at a distance? So how does this help us solve problems?
Well, imagine harnessing that interconnectedness to make qubits work together in a coordinated way. It allows them to explore solutions in a way that classical computers simply can't.
Okay, so we've got these qubits in superposition, entangled, and ready to do some heavy lifting. What happens next?
This is where the variational part comes in. We construct a quantum circuit, which is essentially a series of operations performed on these qubits. Think of it as a recipe with adjustable ingredients.
So we're chefs now. I like where this is going.
Precisely. We have these parameters, like knobs and dials, that we can tweak to modify the circuit and change the output. The goal is to find the perfect combination of settings that minimizes a specific cost function. This cost function is a measure of how good our solution is, whether it's the energy of a molecule or the error in a prediction.
So we're tweaking the recipe, casing the result, and adjusting until we get the perfect dish.
Exactly. And here's where the classical part comes in. We use classical algorithms, the kind running on your laptop right now, to analyze the output of the quantum circuit. And this tells us how to adjust those parameters. It's a constant back and forth between the quantum and classical worlds, iteratively refining the solution.
So VQCs are like a hybrid approach, combining the best of both worlds to tackle those really tough problems.
That's the core idea. And what's fascinating is that this hybrid approach opens up possibilities in a wide range of fields, from simulating molecules in chemistry to building powerful new machine learning models.
Okay, I'm hooked. Let's dive into some of those specific applications. You mentioned drug discovery. I'm really interested in that. So let's start there. How are VQCs being used to revolutionize how we develop new medicines?
You're in for a treat. VQCs, specifically an algorithm called the Variational Quantum Eigensolver, or VQE, are making waves in the world of drug discovery. Imagine being able to design new drugs at a molecular level, understanding how they interact with the body, before even synthesizing them in a lab.
That sounds like something straight out of science fiction, but how does it actually work?
Well, at the heart of drug discovery is understanding how molecules behave. And one of the key properties we need to know is a molecule's ground state energy. This is essentially the lowest energy level it can have, its most stable configuration.
Okay, so why is knowing this ground state energy so important for designing drugs?
Think of it this way: when a drug interacts with a target in the body, let's say a protein, it's all about energy. The drug needs to bind to that protein in a specific way to have the desired effect. And that binding depends on the energies involved.
So if we can accurately calculate the ground state energy of both the drug molecule and the target protein, we can predict how well they'll interact.
Exactly. And that's where VQE comes in. It uses the power of VQCs to approximate this ground state energy. with remarkable accuracy. Remember how we talked about the quantum circuit being like a recipe with adjustable ingredients? Well, in this case, those ingredients represent different configurations of the molecule.
So we're basically using the VQC to simulate different molecular structures and see which one has the lowest energy, which would be the most stable configuration.
You got it. And by doing this, we can gain insights into how the drug molecule might bind to its target, predict its effectiveness, and even identify potential side effects before even setting foot in a lab.
That's incredible. It's like having a virtual chemistry lab where we can test out countless drug candidates without actually synthesizing them.
Precisely. And this could significantly speed up the drug discovery process, making it faster, cheaper, and more efficient.
I'm convinced that VQE has the potential to revolutionize drug discovery.
Yeah.
But what about other areas of medicine? Can VQCs help us in other ways?
Absolutely. Remember our discussion about quantum neural networks, or QNNs?
Right.
These are VQCs that are specifically designed to learn from data, much like the neural networks that power today's AI.
Right. The ones that can recognize faces, translate languages, and even beat us at chess.
Exactly. Now imagine applying that power to medical data. We could train QNNs on massive data sets of patient records, genetic information, and medical images.
So instead of relying on doctors to analyze all that data, we could have QNN sifting through it, looking for patterns and insights that humans might miss.
Precisely. QNNs might be able to detect subtle biomarkers for diseases, predict patient outcomes, and even personalize treatment plans based on an individual's unique characteristics.
That's mind-blowing. It's like having a super intelligent medical assistant that can analyze all the available data and provide doctors with insights that would be impossible to obtain otherwise.
It's certainly a promising area of research, and while it's still early days, there's a lot of excitement about the potential of QNNs to transform healthcare.
Okay, so VQCs are shaking things up in medicine, but I know they have applications in other fields as well. What about something like logistics? You mentioned that VQCs could help optimize delivery routes, which honestly sounds like a dream come true in this age of online shopping.
You're right. Logistics is a field ripe for disruption by VQCs. And the key here is an algorithm called the Quantum Approximate Optimization Algorithm, or QAOA.
QAOA, another mouthful. Can you break it down for me?
Well, at its core, QAOA is all about finding the best solution among a vast number of possibilities. Think about a delivery company trying to optimize its routes. To minimize costs and delivery times, there are countless possible routes, and finding the most efficient one is a classic optimization problem.
Right, and I imagine it gets even more complicated when you factor in things like traffic, weather conditions, and delivery windows.
Exactly. Classical algorithms often struggle with these kinds of complex optimization problems, especially as the number of variables grows. But QAOA leverages the unique capabilities of VQCs to explore these vast solution spaces more efficiently.
So it's like giving the delivery company a quantum-powered navigation system that can sift through all those possible routes and find the absolute best one.
That's a great way to put it. And it's not just limited to delivery routes. QAOA can be applied to a wide range of optimization problems, from portfolio optimization in finance to resource allocation in energy grids.
It sounds like QAOA could have a massive impact on businesses and industries around the world. But let's be realistic. Are we really at the point where these quantum algorithms are outperforming classical methods?
That's the key question. And the honest answer is, it's still a bit of a mixed bag. For some problems, QAOA is showing promising results, even on the relatively small and noisy quantum computers we have today. But for other problems, classical algorithms still hold the edge.
So it's a race between the quantum and the classical, and we're still in the early innings.
Exactly. The field is evolving rapidly, and it's too early to declare a clear winner. But the research is incredibly exciting, and we're constantly learning new things about the potential of VQCs and how they can be applied to real-world problems.
This has been an incredible journey so far. We've seen how VQCs are revolutionizing chemistry with VQE, bringing the quantum advantage to AI with QNNs, and tackling complex optimization problems with QAOA. It's clear that VQCs have immense potential. But I know there are also challenges and limitations that need to be addressed. What are some of the biggest hurdles that are holding VQCs back from reaching their full potential?
Well, one of the things we're grappling with is something called vanishing gradients, or sometimes you hear it called barren plateaus.
Barren plateaus.
Yeah, it's a bit of a technical term, but basically what it means is that as our quantum circuits get more complex, it becomes harder and harder to fine-tune those parameters we talked about earlier.
So it's like trying to adjust a recipe with a million ingredients where even the tiniest change can throw everything off.
That's a great analogy. It becomes really difficult for our classical optimizer to figure out which way to go. It's like wandering around in a vast, flat desert with no landmarks to guide you.
So how do we escape these barren plateaus? Is it a case of needing more powerful quantum computers? Or are there other solutions in the works?
It's a bit of both. We definitely need more powerful quantum computers with more qubits and lower error rates. But researchers are also developing smarter ways to design those quantum circuits, so they're less susceptible to this problem. It's like designing a recipe that's more forgiving, where small tweaks don't completely ruin the dish.
Makes sense. But even with those improvements, there's still the issue of the quantum computers themselves, right?
Yeah.
We're not all going to have quantum computers on our desks anytime soon.
That's true. Building and maintaining quantum computers is a huge engineering challenge. They're incredibly sensitive to their environment, and even the slightest disturbance can disrupt those delicate quantum states. It's like trying to build a computer out of snowflakes.
Wow, that's a powerful image. So it sounds like there's a lot of work to be done on both the hardware and software fronts before VQCs become mainstream. But even if we solve all those practical challenges, there's still a bigger question looming. Do we even know if VQCs will always be better than classical algorithms?
That's the million-dollar question. We're still in the early days of exploring the power of quantum computing, and we don't have all the answers yet. It's possible that for some problems, classical algorithms will always be more efficient or practical.
So it's not necessarily a case of quantum computers replacing classical computers, but rather finding the right tool for the right job.
Exactly. It's about understanding the strengths and limitations of both approaches and figuring out how to best combine them.
Well, this deep dive into VQCs has been a real eye-opener. I've gone from feeling completely intimidated by quantum computing to feeling genuinely excited about the possibilities. So thanks to Jörg Oschnepat and his essay for giving us a glimpse into this fascinating field.
My pleasure. VQCs are a powerful new tool with the potential to revolutionize countless industries and solve problems that were once considered intractable.
And who knows, maybe one day we'll be looking back at this conversation as the moment we first glimpsed the dawn of the quantum age. To our listeners, thanks for taking this deep dive with us. What seemingly impossible problem would you want a VQC to solve? Let us know. And until next time, keep exploring.